Some of you, I'm sure, are going to wonder about, have I graded the midterms? I have not. I'll be grading them, I think, over the weekend and have them back to you on Tuesday. So I don't have any comment about that. So let us talk about averaging theory. That is, we've been talking a bit about nonlinear oscillators, and we spent some time on the van der Pol oscillator. You'll remember we did the case of strong nonlinearity, where we had the relaxation oscillator limit of the problem. And then I think in our previous discussion we looked at an energy method for the weakly nonlinear case. But I sort of described that as a crude method, which it is. And today I want to show you a much improved method, which will give us a lot more information than we got from the energy method. This technique that we're going to use comes up a lot in dynamical systems, and so I'll try to clarify some of the conceptual points of averaging theory. You'll, I'm sure, see it in more advanced courses too. So, incidentally, the discussion of averaging theory that I'm going to give is not in the book as the main text. So in 7.6, I do an equivalent theory. That is, you can show that they give the same results, called the method of two timescales, or sometimes called two-timing, which sounds sort of silly. Anyway, so the two-timing method is how I approach it in the book. This averaging theory that I'm going to describe is, I think, in one of the exercises in the book, but I didn't assign it for homework, so you probably won't see it unless you pay attention to it here. Okay, anyway, so averaging theory, what's the idea? Well, let's consider systems that look like this. X double dot plus X plus epsilon times a function of X and X dot equals 0. So that is, we've got the first two terms look like simple harmonic oscillator, where we've chosen the time scale to be normalized in such a way that the simple harmonic oscillator on its own would have angular frequency of 1, period 2 pi. But then there's this small correction to it, epsilon times some function of X and X dot. So this includes the van der Pol oscillator as a special case. So this epsilon term is supposed to be very small. And so this is what we mean by weakly nonlinear. It's a small perturbation of a linear harmonic oscillator. We could also allow this to depend on time, but for today, let me just stick to the case where it's just X and X dot. So it's an autonomous system. You could regard it as a perturbation of a harmonic oscillator. And there's a whole, vast body of theory about how to do perturbation theory. You may have run into it in quantum mechanics courses or other nonlinear vibrations courses. The point of view we're taking in this course is that we don't spend much time on perturbation theory. This is probably about the only example I'll be showing you. But if you were taking this course in the 1950s or 60s, you would have spent 14 weeks on perturbation theory. And you can still take a course like that. If you take the nonlinear vibrations course from Professor Rand, it's pretty close to that point of view. So anyway, here we are. We have this system. Now, we know that when we write it as in the phase plane, it would look like, let's say we write it as X dot equals Y, Y dot equals negative X plus epsilon H of X and Y. And in the simple case when epsilon is 0, we know exactly what happens. We'll get solutions of the form X as a function of t is r cosine t plus phi, and the y of t will be minus r sine t plus phi, where R represents the amplitude of the oscillation, and phi is the phase angle, and both are constant for the ordinary harmonic oscillator. So that's just writing the harmonic oscillator in polar coordinates, if you want to think of it that way. And not really, actually. Maybe best to just say, I mean, we know it has sine and cosine solutions of constant amplitude. So I'm choosing time, the origin of time, in such a way that I can write it this way. Yes? We're thinking, we always, are going to treat epsilon as positive. Or let's say greater than or equal to 0. Did I screw that up? Oh, yes, I did. Thank you. Yes, that's right. That's minus. Yeah, thanks. Sorry about that. Yes. So anyway, R and phi are constant, I guess I should say, on trajectories. Meaning as the system evolves on a given trajectory, R and phi will stay constant. Now, of course, we're interested in the case when epsilon is not 0, but small. And so when epsilon is not 0, we expect very slow evolution or a slow drift of these quantities R and phi that were previously constant. Right, that's going to be the effect of the small nonlinear term, the epsilon term. These constants R and phi will start to evolve. They won't be constant anymore. Like, for instance, we might evolve, the whole system might approach a limit cycle. And so what we want to do today is figure out the evolution equations for the amplitude and phase, given the effect of this nonlinear term h. Still, we do know that because epsilon is small, the trajectories will be nearly circular, and they will have nearly period 2 pi, because the epsilon term can't do very much. It's only size epsilon perturbation to the vector field. So, but trajectories will stay nearly circular. With period, I hesitate to call it period because they're not exactly closed, so they're not really, they don't have a period. But you know what I mean, with a period, nearly 2 pi. And that was the kind of intuition we used in the energy method, but we can now make it more precise today. Okay, so let's try to figure out evolution equations for the R and the phi. Here comes a step that many people find confusing, so be sure to ask me if you don't get what I'm saying. I'm going to let x of t equal r cosine t plus phi. And I will let y of t equal minus r of t. Maybe I should write it with the explicit t in here. Actually, it'll look better. That is, the phi and the r are no longer regarded as constants. They're not constant. So I have r of t, phi of t, and in here minus r of t sine t plus phi of t. And what's confusing about this is, at first glance, it just looks like I'm doing calculus wrong. That is, up here I said x dot is y, and if the r and the phi depend on time, then you can see that the time derivative of x will not just be y, because obviously there will be contributions from terms like r dot and phi dot, so I've left out all kinds of terms. Yes, that's true from one point of view, but the way you should think of this is, suppose I have x and y as solutions of this system. I can define variables r and phi by this definition. That is, this is really more a definition of r and phi than a statement about calculating derivatives. So view this as a definition of the r of t and phi of t. If you want, you could think of it this way. You could think of r of t as being just defined as square root of x squared of t plus y squared of t. And similarly, you could think of tangent of t plus phi of t. This is defining phi as minus y of t over x of t. And I'm allowed to make those definitions, and I, in fact, have just made them. So there's no contradiction or anything. This is okay. We're going to then impose these differential equations, and that will allow us to derive our evolution equations for r and phi. Okay, so are you with me so far? That's an allowed definition of these quantities, r and phi. Fine, so then let's allow that and do it. And now what good does it do for us? I mean, maybe before I say that, you want to think about it physically for a second. This is like going into a rotating frame where you're moving with the trajectories of the epsilon equals 0 system. So it's sort of like, how does the system, if you imagine two problems, one with epsilon 0 and one with epsilon not 0, start them from the same initial condition, and you sort of view what's happening from the point of view of the epsilon equals 0, the unperturbed system, then that will allow you to sort of freeze out the uninteresting motion and watch the interesting part, which is the slow drift of the r and the phi. Okay, well anyway, so let's now find the equations for r dot and phi dot. Well, the easiest way is using our definition for r. We have r squared is x squared plus y squared. And I had mentioned this trick in polar coordinates earlier in the course, that this is a nice way to derive evolution equations for r. Differentiating both sides, we would get r dot is xx dot plus y dot. And then substituting, that's x. We said x dot is y. And then y dot is negative x minus epsilon h, where this time I did remember the negative sign in front of the epsilon. And so then multiplying that out, we end up getting, it looks like I'm getting negative epsilon yh, because the yx terms cancel out. And then I have a definition for y, which has this negative sign in it. And so then this becomes minus epsilon h times negative r sine t plus phi. So those negatives cancel out. And actually, we can cancel out if there's a negative. We can cancel out this r with that r. And we end up getting r dot is epsilon h sine t plus phi. And let's put that in a box. That's one of the equations we were shooting for. We're not done yet, though. But the other, we need an evolution equation for phi dot. And so maybe I'll skip the algebra. You could check your understanding of all this. What you would do to derive an evolution equation for phi is you could take this formula for right here. Actually, it's probably best to write it as t plus phi equals inverse tangent of negative y over x. Differentiate both sides. Remember how to differentiate inverse tangent. Anyway, do those steps. You'll end up getting this. Maybe I'll just write that down. Similarly, using d dt of tangent inverse of negative y over x equals d dt of t plus phi of t, you get this equation for phi dot. You'll get phi dot is minus epsilon h, sorry, no minus, just epsilon h over r cosine t plus phi, and then that gets its own box. Okay, so check the algebra on that. Nice, it's kind of symmetrical in a way. That is, the r dot equation is very analogous to if we did r times phi dot. The only difference being that this has a sine and that has a cosine. Is there any questions so far? Okay, so we have those equations. Now, you can observe one thing that's nice about them. They are both order epsilon. It says r dot is epsilon times something, and phi dot is epsilon times something. And that should make sense to you, right? That's saying that r and phi dot are both very small, meaning they're changing slowly. R and phi are slowly evolving. That's what we said would happen based on the intuition earlier. So we have slowly varying amplitude and phase as expected, in the sense that r dot is of order epsilon and phi dot is also of order epsilon. Now, if you're really on top of this, you might notice that we've done something a little strange. Let's just stare at this for one more second. In the notation, I've sort of buried some of the complexity. I've written h, but let's think about h for just a second. H is a function of x and y, which means in these new variables, it's a function of r cosine t plus phi and of negative r sine t plus phi. And so h is explicitly time dependent. It has t right there in it. Right? This is now a non-autonomous term. So we've made our system non-autonomous. That is our system for r dot and phi dot. Non-autonomous, that is to say, explicitly time-dependent. And, you know, you might say, great move, genius, you made the problem worse. Right? That's no good. Why would you do that? You had a perfectly autonomous system. The arrows in the phase plane, the little vectors were all frozen. They weren't wiggling. Now they're wiggling. You can't even do phase plane analysis on this anymore. So, well, that's true. We have done all that. But it's going to turn out still, it was a good thing that we did, and we can cope with this in a way that gets at the heart of what averaging theory is about. That is, we're going to exploit the separation of timescales between the stuff which is evolving on, let's say, fast time, meaning time of order 1. I'm speaking here of the oscillations that take time 2 pi to go around, about. That's fast. Versus stuff that is changing on a very slow time scale, which is the amplitude and the phase. Those do not change much on a time scale of order 1 or 2 pi. They only change by an amount epsilon in that amount of time. So if you want them to change by some substantial amount, say order 1, you have to wait an enormous time of order 1 over epsilon. So you have these two very different time scales, the slow time scale of the amplitude and phase and the fast time scale of the oscillations. And we've really brought that out with this transformation, and that's going to be the thing we can exploit to solve the problem quite quantitatively after this. I saw a question. Yes?
Why didn't you say it was non-autonomous when T was already there?
No, it's certainly non-autonomous when I look at these equations also. I just mean that when I looked at the x dot, y dot equations, I guess I shouldn't have said it that way. It's not that we made our system for r dot, phi dot non-autonomous. What I really mean is we've made our system, which used to be for x and y. That had no time in it. So, right, I shouldn't have said it like that. I just mean we made the dynamical system non-autonomous in this set of coordinates by going into this rotating frame. But it's okay. Yes, thank you. That's better to say it that way. Is there another comment? Okay. So, now what? As I say, we're going to exploit the separation of timescales. That is the fast oscillation versus the slow drift. To get a lot of information. And so this is where the really cool conceptual point comes in. That if you haven't seen this before, I think you're going to like this. But it does require some concentrating to really get it and make sure you believe it. And if you don't, please ask, because this is really the key new idea. What we're going to do is iron out the fast oscillations. By averaging over one cycle. You know, I said it was called averaging theory. It's because of this operation that we're going to be doing throughout. We'll average over one cycle of the fast oscillation. Over one cycle of length 2 pi. So to do that, let me introduce some notation that we'll be using quite a bit. So if I have some function g of time, define the average over one cycle, where actually I want this average to be centered on a point t. So average over one cycle about the point t as, I'll call it g bar of t. So the bar means average. Sometimes, though, when I want to think of averaging as an operation, I'll use angle brackets. So I might also write it like this, the average of g regarded as a function of t. And the definition is it's 1 over 2 pi integral from t minus pi to t plus pi of g. Now, I shouldn't really write t again because this is a dummy variable of integration I need. So I'll write something like g of s ds. Although among grown-ups and professionals, there isn't much danger in calling a g of t dt. But, you know, your freshman calculus teacher will have a conniption if you do that. So, okay. So whatever, we may or may not use t for this, but officially we should be using some other variable that we could call s. So this is a running average, right? I mean, if you take statistics or something, you think this is a moving average. It's an average which is sliding along as t changes. The window is a window centered at t, and it goes back by minus pi and forward by pi. And so we're taking, like, you know, if you ever, I don't know if you have any money yet, but if you did have some money, you could put it in the stock market. Not saying you should. I'm not making any investment advice. Just if you did, or the bond market, or pork bellies, or whatever, you could invest. And then, you know, while you're busy checking the financial pages or looking on the internet at stock charts, you will see running averages all over the place, right? I mean, do you know what I'm talking about? You've seen these? Yeah. So to iron out the fluctuations, you look at, say, the average over the past month or whatever. So that's what this thing is doing. It's looking at the average over a cycle, but that the center of the cycle keeps moving. So that's the kind of concept we want. Is there any question about what I mean by this running average? I want to make a little analogy that I might refer to now several times in the rest of the lecture, which I hope will give you the right intuition. Think about how tall you are. Okay, so you don't have to tell, but just keep it in your mind. And now think about, that of course is changing over time. So obviously when you were a little baby, you are not as tall as you are now, probably. And then as you grew, you got taller. So your height is a function of time. But it changes on a time scale of, well, that's a tricky point, actually, biologically. They tell me that it changes during the course of a day. That when you wake up, you're a different height than when you go to sleep because of the gravitational compression on your body all day long. Let's ignore that. Let's just focus on the growth aspect, which is that when you were little, you were shorter, and now you're taller. So obviously your height has changed over a time scale of months or years. But I want you to think about how much your height changes during the breath you just took. Okay? You just took a breath cycle. And your height changed during that time. Now, you don't think it did, because it didn't change much. That's the kind of thing that I want you to think about. That is, you have a fast time scale, one breath cycle, maybe a second. And then you have the time scale for your height to change, which is months or years. Notice they're very separated time scales. That's what's going on in this kind of problem. That I have a quantity which is changing slowly, like, say, the r or the phi. Think of that as like your height. If I take its running average over one fast cycle, like if I ask you, what's the running average of your height over this cycle and the next cycle, it seems like a stupid question. Your height is not changing on that time scale. So your running average of your height is basically indistinguishable from your instantaneous height. Obvious? That's what we're going to use, that intuition, a lot. And so I'm going to frequently replace variables by their averages. And you might, if you're thinking mathematically, get worried about that. Whoa, professor, one's an average and one is not. Yes, but it's obviously true that they're almost the same because of the separation of time scales, like the height over one breath cycle. So let's get into the guts of that now. Do you want to ask a question about that little riff? Yes?
When this assumption is true, how large can the error get?
Good. There's a good question. How large can the error get, given that this is not exactly right? How big is the error? The error will be proportional to epsilon. So that is, the running average will differ from the instantaneous quantity by an amount that goes to 0 proportional to epsilon. So it's roughly speaking, it's an order epsilon error on one cycle. Right? Because r dot and phi dot are order epsilon. So over a time of length 1 or 2 pi, they can be different from their average by an amount proportional to epsilon times an order 1 quantity. So it's a very negligible amount, but it is there. So I'll keep track of that error as we go. I mean, I won't ignore it. I'll included as we discuss this. This method, I don't know, I think it was invented maybe around like in the 1930s or so by various people in different parts of the world, in Russia and some in America. Van der Poel himself had these kind of ideas. For a long time, it was just the kind of intuition I'm giving you here. Then later dynamical system theorists proved theorems about it. So if you read the book by Guggenheimer and Holmes, you can see averaging theory as a theorem. I mean, there is a real theorem here. It's not just intuition. But I'm just giving you kind of the old school intuitive way of thinking. All right, so anyway, having given this definition of running average, I want to notice one key fact about it, which is that suppose we take the average, the running average, and then we take the time derivative of the running average. So I do g bar first, then I do dot. Does it matter? What if I did g dot first, and then I did bar? They turn out to be the same. So you can either take the time derivative of the average or the average of the time derivative, and they're the same because just do the calculation. So g dot bar would mean I take the average of the derivative. So I'd go t minus pi to t plus pi of the derivative dg ds. And when you evaluate that, you'll get 1 over 2 pi. So I'm integrating a derivative. So I'll just get g at the upper limit, t plus pi, minus g at t minus pi. And on the other hand, if I do it this way, g bar dot, let's see, what would I do? I'd go d dt of g bar, so that's 1 over 2 pi integral from t minus pi to t plus pi, g of s ds. And now you have to remember how to do a time derivative of an integral which has limits that depend on t. And that's something you're supposed to have learned. That's one version of the fundamental theorem of calculus. So that will end up giving you 1 over 2 pi, and then you plug in g at the upper limit minus g at the lower limit. So it's the same thing as we wrote above. So by the fundamental theorem of calculus. So, okay, so it doesn't matter whether we take the dot first and then the bar, or the bar first and the dot. And we're going to use that because I want to take those equations I wrote down for r dot and phi dot, and then I want to do running averages on them. And you'll see why. It's going to get, remember I said I sort of did this goofy thing where I made a system non-autonomous. By doing the running average, we can end up getting rid of that. We can convert this to a phase plane problem with no time dependence in it explicitly. So watch how that goes. What we want to do next is derive the equations for r bar and phi bar. Right, we already had equations for r and phi, the instantaneous changes of the amplitude and phase, but now we want to get the differential equations for their average values over one cycle. And those will turn out to be very nice. So let's see what we do. We have r dot, take its bar. That's the same as r bar dot from the argument we just made. But r dot bar would mean we already derived an equation for r dot. It was epsilon h sine of t plus phi. Right, that was r dot. So now if I take the average of it, I could put a bar over the whole thing, but that looks kind of goofy. Let me just do it with my slick angle bracket like that. Where the average, in case there's any ambiguity, means with respect to the variable t, we're averaging in this way that we talked about, the 2 pi running average. Okay, and then similarly, I have phi dot bar is phi bar dot is, from that earlier formula, the average of epsilon h over r cosine t plus phi. And everything is exact still. We haven't made any approximation yet. And there's now a subtle difficulty that's easily overcome. But do you see why these are not quite what we want yet? I mean, you want a dynamical system where R bar and phi bar, their evolution would depend on their current values. Right? I mean, that's how we like it to be. R bar and phi bar should depend on themselves. But notice that there are no R bars and phi bars on the right-hand side. We just have ordinary R unaveraged and ordinary phi. So this is exact since the right-hand side depends on R and phi, not R bar, phi bar. So now we want to invoke that idea that I mentioned about your breath cycle. That is, it's sort of silly to distinguish between R and R bar. That's, again, like saying how much is your height right at this instant versus how much is your height averaged over your past breath cycle. They're sort of the same thing with a tiny error. So that's where we're going to introduce our approximation. We will now replace every place we see R, we're going to write R bar. And that incurs some error, but not much. So over one cycle, R equals R bar plus an error of order epsilon. Same thing with phi. So let's make this substitution. Let's replace R and phi by R bar, phi bar everywhere. Now let's keep track. What kind of error will that introduce? Notice that there are these epsilons in the equation. So when we introduce an error of order epsilon into the R and phi, that order epsilon error will end up multiplying this epsilon, and we'll end up getting an order epsilon squared error in the differential equations. In the ODEs. So that's okay. It's negligible compared to the leading term, but we'll just keep track of what that error is. But the beauty of it is that we now get autonomous equations that we can analyze with phase plane methods. We can analyze with our geometric methods of the phase plane. And a key principle in all of this is that we will regard well, actually, maybe I'll say that. I was going to say we're going to regard R and, or R bar for that matter, we'll treat them as constants with respect to fast time. So when I'm computing integrals, I'm going to treat those things as constants, not time-dependent functions. It's again like saying that your height is not changing. It's a constant over one breath cycle. Not only is height instantaneously equal to the running average, approximately, but both are approximately constant. They're not changing much on a short time because they change only on a long time. So that's another heuristic that, another little principle that comes into this. Let me do an example to show you what I mean. So just to quote that for the record here, I said I'm going to replace R and phi by R bar, phi bar everywhere. Treat R bar and phi bar as constants when performing these averages. Anything that involves one of these averages over one cycle in t. Okay, so let's do an example then. How about we go back to our van der Pol oscillator? We had talked about that with the energy method, and now time to wheel out this method on it. So that was the equation, x double dot plus x, plus it had this interesting nonlinear damping, epsilon x dot x squared minus 1 equals 0. So in our current notation, then the h is the term multiplying the epsilon. That's x dot x squared minus 1, which we would write as y times x squared minus 1. And then remember our R and phi definitions. So the y would become minus R bar. Well, actually, okay. So y is supposed to be minus R sine t plus phi. But because I want everything to be in terms of the barred quantities, and I said that R bar is effectively the same thing as R, I put bar there, and I put a bar on the phi. So this term is y. And then x squared minus 1 will be R bar squared cosine squared t plus phi bar. And then I have minus 1. From that minus 1. So that's my h, and I've made an order epsilon error by doing all these replacements of variables with their bars. So that's my h, some messy thing. And notice it is explicitly time dependent through the t. And also, on the slower time scale through the R bar and the phi bar. Want to ask anything? Still with me? All right, next, let's get into the averaging part. By the way, when you use this method, you don't have to, of course, go through all this derivation. Now that we've done the derivation, it's done. And so in practice, I mean, this can be really fast, and you can do on the back of an envelope and impress people with what you know about nonlinear. Not that anyone will care, of course. But I mean, you could really solve nonlinear oscillation problems very efficiently with this technique, if they're just small perturbations of a harmonic oscillator. Okay, so I wrote down H. Now, where do I go from there? Well, that tells me that R dot. Okay, let me be pedantic for a little while longer. I mean, you can tell I'm itching to stop putting bars on everything. Maybe you are too. We could stop right now if you want. Should we stop? We could stop. All right, let's go wild. So we will stop writing bars, even though we know that they're there. Or should we? I don't know. It feels kind of risky. You want them there, don't you? You're a careful guy. I can see that. All right, I'm going to keep the bars on a little longer until you're really sick of them. Okay, R bar dot is average epsilon H sine T plus phi bar. Close the average. And then, remember, we said that because of this prefactor of epsilon, plus the order epsilon error that we made, in our H, we're now getting that the differential equation has an order epsilon squared error. Okay, very good. And now let's put in everything in sight. That is, expand out the H. So I have epsilon. The H is that sucker that we wrote up there. So I get R bar. There's a negative sign, isn't there? So let's put that in. Negative epsilon for the negative in front of the H term. Negative epsilon R bar sine. There's a sign here and a sign way up here. So I'm going to get sine squared. T plus phi bar. And then times this factor that's in the square brackets. R bar squared. Cosine squared T plus phi bar minus 1. Close the square brackets, close the angle brackets, and then plus order epsilon squared. Okay, we're cooking now because we're now at a point where we can compute averages. That is, stare at the big expression here in the angle brackets. What are we supposed to do next? We're supposed to compute averages. That means integrals from t minus pi to t plus pi. And what am I averaging? I'm not averaging R bar because that's a constant. Okay, that was this principle. You treat R bar as a constant in the averages because it varies so slowly. So R bar is a constant. That can come outside the average. Phi bar is also a constant, again, in this intuition. So what we're really looking at is, let's factor out the minus epsilon R bar as constants. And then in here, I have R bar squared. Again, it's a constant, this thing, times an average of sine squared cosine squared. I'll just write it that way. I don't need the argument so much because any average of sine squared cosine squared over a whole cycle, it doesn't matter where that cycle is centered. As long as the average is of length, over an interval of length 2 pi, which is what we're doing. So I'll just write it that way. And then minus, what else is there? I have a 1 times a sine squared. So this subtraction says I should be doing an average of sine squared. Close that, and then plus order epsilon squared. Okay, now we have to understand how to do averages. Let's just think about them for a second. Depending on your background, you either instantly know the values of these averages or you're sort of puzzled about what are you supposed to do. So let's look at average of sine squared. What does that mean? According to the definition, it would be 1 over 2 pi. We'd go integral t minus pi to t plus pi. What? Then I'd go sine squared of s, being really careful, ds And anyway, I don't know. I mean, do you know what this is? You want me to do more? I don't want to do it too painfully. Can I give you, okay, it's a half. Now, how do I know that? There's a lot of ways to know that. So here's one way you could, let me give you the intuition, why it's a half. I mean, okay, if you don't know this, you can always do it by using the double angle formula. You could say cosine of 2u equals, what is it, 1 minus 2 sine squared u. And then you could replace the sine squared with the 1 minus cosine 2u and brutally calculate the integral, and you'll get 1/2. But there's a reason it's a half. And the reason is, draw the picture. So what does sine squared look like? Let's suppose we started it at a place where it's 0. That is like, and sine squared is a function that's never negative, and it just goes like this. Keeps going and going. Now, how often is it 0? Sine at 0 is 0. Sine at 2 pi would be 0. So it's, the distance between the zeros is pi. So here's another pi to here. And we're averaging over something of length 2 pi. So now, what is this maximum? 1/2. That's 1. That's 0. And now I'm claiming that the average value of this object is a half, which sort of looks right by the symmetry. But let's think about it. I mean, what is the average supposed to be? The average means if I drew this rectangle, I could ask how much area, because we're computing an area. So how much area is under sine squared? How much area relative to the whole rectangle? Can you see that that's exactly half the rectangle? Right? Isn't that clear by the symmetry of the picture? That is, if I do this, that's a puzzle piece which is exactly the same shape as that puzzle piece. So this occupies half of this box. This occupies half of that box, and so on, blah, blah, blah. So it's 1/2 the area of the whole box, which is 2 pi times the height, which is 1. So the area of this box, this integral of sine squared is pi, but then I'm dividing by 2 pi. So I'm getting a half. There's another way to see it. Because if you look at sine squared, it's the same shape as cosine squared. It's just translated. Right? I mean, they're off by pi over 2 or something like that. So if you accept that whatever the average of sine squared is, it's got to be the same as the average of cosine squared, then, on the other hand, their sum is equal to 1. Sine squared plus cosine squared is 1. So the average of sine squared plus cosine squared is the average of 1, which is 1. But this is 2 times the average of sine squared. So that's another way to see why it's a half. There's a bunch of ways. So just brutally doing the integral doesn't show any sex appeal. No finesse. No style. That's really what I mean. No style. So these are stylistic ways. Okay. But anyway, for harder ones, you might need to actually do some integrals. But I would say you should just commit to memory, or this way of thinking, that average of sine squared is a half over any, whole number of these, quarter cycles or something. And we can also we have to do the average of sine squared, cosine squared. Well, for that, we can remember that sine of 2u is 2 sine u cosine u. So in fact, doing an average of sine of something, cosine of something, like say sine u, cosine u, that's the same as doing an average of 1/2. 1/2 sine of 2u is sine u cosine u. So doing an average of this object squared an average of sine squared cosine squared. If I square both sides, I'm getting 1/4 an average of sine squared of 2u. But it's still just an average of sine squared. So it's going to be 1/2, like we just argued, times 1/4. So we're going to get 1/8. So again, you can do those integrals by hand if you want, but the quick answer is that these averages come out to be minus epsilon r bar squared. This one I know is 1/8. Minus, this one I know is 1/2. And then plus, I think I've lost an r bar somewhere. Oh no, it's outside. Okay, I'm good. And then plus order epsilon squared. What was all this? This is all the equation for, I seem to have lost my antecedent, as they would say in English class. This is r bar dot, right? Isn't that right? Yeah. So any question about the manipulations? Yes?
How come we're not carrying the order epsilon from h?
Sorry?
How come we're not carrying through the order epsilon from h?
How come we're not carrying through the order epsilon from the h, aren't we? I think we are. So when I say plus order epsilon correction in the h, when I wrote in here r bar dot, it was this thing. I mean, h is all built in here, right? So if I put in plus order, oh, I see. So you want me to say this and then plus order epsilon inside the square bracket. Yes, you could do that, but then that order epsilon times this epsilon makes order epsilon squared, and I just lumped it into the garbage can out here. Yes, that's right. It's implicitly there. That's why it's been dumped in that pail. Is there another question? Okay, so we've got our equation for r bar dot. Now we can just start enjoying ourselves. That is, we've got this beautiful evolution equation, let's clean it up a little, that says that the average evolves according to just epsilon r bar. Let me factor out an 8. And then this becomes 4 minus r bar squared plus my annoying garbage pail there. So let me from now on neglect this. This is tiny compared to the other. And the dominant effect is governed by this little first order nonlinear differential equation, which we can analyze with our, I mean, if we want, we could draw geometrically that r bar dot versus r bar, that the graph of this shape is, it's a cubic curve. It goes up at the origin and goes down, crosses through at 2. For r bar, and of course we're flowing to the right here and we're flowing to the left here, and this is a stable fixed point. There's an unstable fixed point at r bar equals 0. So what it's telling us is that the origin, which remember means zero amplitude oscillation, is unstable, and the system approaches r bar equals 2 as t goes to infinity. And you'll remember, I hope, from our energy method argument that the van der Pol oscillator does have a limit cycle of amplitude 2. That's the 2. So that's the amplitude of VDP I'm writing for van der Pol oscillator as epsilon, for epsilon much less than 1. But what's really good about this method is we can say much more than this. That is, we don't just have to say that the long-term behavior is to go to a oscillation of amplitude 2. We have the whole time evolution in this differential equation. So if we feel like solving it explicitly, which we could, it's not that hard, we can see in a lot of detail how the amplitude builds up or decays to 2. So let's just suppose, I'm not going to show the details, but if you want, you could check that if you had, say, x of 0 equals 1 and x dot of 0 equals 0 as an initial condition, then that corresponds to an r bar of 0 equals 1. And you just solve the ODE, which you could do by partial fractions. Solve the ODE for r bar. And you'll get this cool formula. R bar as a function of t is 2 over square root 1 plus 3 e to the minus epsilon t. I got that by solving this differential equation by separation of variables and using partial fractions on it to do the integral. So you get that. So that's the evolution of r bar. Notice as t goes to infinity, this e to the minus epsilon t term goes to 0, and you just get 2 over 1. So it goes to 2. But it gives you the whole time dependence. Also notice that the time dependence is very slow. It's going e to the minus epsilon t. It takes time of order 1 over epsilon to do anything substantial, which we already know. But it's there explicitly. And finally, you could even convert this into, well, actually, maybe I ought to say something about the phase. Let's just quickly do the phase. And then I'll make another point. That is the phase. So we had phi bar. I'm going to now drop the overbars. That is, I'm not going to write phi bar anymore. I won't distinguish between phi and phi bar. Anyway, phi dot would then be average of epsilon h over r cosine t plus phi. And I'm also going to neglect the order epsilon squared correction term. So then what does this boil down to? It's going to be epsilon over r. I substitute my h. So I'll get, well, let's see, average minus r sine t plus phi times r squared cosine squared t plus phi minus 1. And then times this cosine of t plus phi that's sitting in the formula. And that's it. Then close the average. I don't think I can go on to the sacred third board yet. We still have enough time. Maybe get one more board worth. So let's see, what are all those averages? I think after you clean it all up, you'll get that equals minus epsilon. You can cancel out some factors of r. There's an r in the denominator and an r up there. And looks like I'm getting minus epsilon r squared average of cosine cubed sine minus average of sine and cosine. And so all these are averages over 2 pi, intervals of length 2 pi, and they're 0, actually. Like, if you did cosine cubed of u sine u du, I hope you can believe me that it doesn't matter about centering at t. You could center at you can just shift coordinates to end up converting it to this kind of integral. And you can see that this would give me something like cosine to the fourth. This is what am I trying to say? If I think of this as v cubed, this term is what, negative dv? Isn't that right? So we would get something like minus cosine to the fourth of u going from 0 to 2 pi. That gives 0. And so I've just memorized that this average is 0 and this one is also 0. And so you end up getting that the whole thing is 0. Now maybe we should remember there is an order epsilon squared error in all that. So what did we conclude? That phi dot is order epsilon squared, which is interesting because it says, even though we knew initially that phi would change on the slow time scale, actually it changes on an even longer time scale, a super slow time scale, which is that phi changes, phi is basically constant until you get to time scales of order 1 over epsilon squared, which are really enormous. So you could think of that as saying that the period of the van der Pol oscillator is essentially 2 pi with a very tiny correction. That is, this, you can check that this implies that the period of van der Pol will be 2 pi plus, instead of the order epsilon correction you would expect, it's only going to have an error of order epsilon squared, much smaller. So roughly speaking, the nonlinear term in the van der Pol is mainly changing the amplitude. It's not doing much to the frequency or the phase. That's at a higher order of perturbation theory that it's doing anything. So that being said, we can now make this interesting comment about the solution of the van der Pol, which is that to the order of perturbation theory that we're working, we have, we know that x of t was defined as, or the r and the phi were defined so that x of t is r of t cosine t plus phi of t. And so with our exact calculation for r bar now, I'm replacing r by r bar, we're getting 2 over big square root 1 plus 3 e to the minus epsilon t cosine of t plus, we could pick initial conditions so that the phi is just 0. You could really just write it as cosine of t. With the initial conditions I did pick, actually, where did I say them? Up there. X of 0 is 1. X dot is 0. That makes it just be cosine of t with no need for a phase angle. So we just get x of t as this plus our order epsilon correction. And that's a pretty cool function. If you draw that, you'll see a picture that looks like this. X as a function of time starts at an amplitude of 1, asymptotes up to 2. But, and also let's draw a -1 and -2. And you have this very slowly changing envelope that looks something like this. And then likewise down here, it's just the mirror image. And then inside, you have these fast oscillations. That are all, period 2 pi more or less. So that's what the solution of the van der Pol looks like with those initial conditions. It just starts at 1 and then slowly builds up to 2. But we have, as I say, this nice analytic form thanks to the method. Is there any question about the argument? It's pretty powerful. Let me give you one more example and then we'll quit. So here's another famous nonlinear oscillation. called Duffing's equation, except I think that's a mispronunciation because there's a German mathematician or engineer. So I don't know. I don't speak German. It might be something like Duffing, or does anyone speak German? Duffing. I don't know. Anyway, everybody around here says Duffing. So the Duffing equation, as another example, is what happens if you have a small cubic nonlinearity in the spring. That is, instead of a perfectly linear spring, what if I have a x cubed term in there, but small? So you can think of it as a spring. If you think of the ordinary Hooke's law, where force versus displacement would be a straight line, so that's Hooke. That's the simple harmonic oscillator. If we have a positive epsilon in here, that would mean that the spring starts like this, but then actually gets stiffer. That is, as you stretch it more, it gets stiffer. So people talk about a hardening spring when epsilon is greater than 0. Versus if epsilon is negative, you have a softening spring. It gets less stiff as x gets bigger. So anyway, this raises this interesting point. What happens if you have a spring whose stiffness changes as you stretch it? Well, just cranking out our equations here, this is what I mean by back of the envelope. Knowing that the h in this problem is just x cubed, then this becomes r cubed cosine cubed of t plus phi. And so if I ask what happens to r dot, it's going to be the average of epsilon h sine t plus phi. Again, ignoring all the details with the epsilon squared and stuff. So this is average of epsilon cosine cubed sine. And I guess I have an r cubed coming outside. But this average we already know is 0. We talked about cosine cubed sine. So in fact, r dot does not change. R dot is order epsilon squared. That is, the Duffing equation does not cause a change in amplitude to lowest order, only on a longer time scale. That is, r equals a constant at this order in perturbation theory. But the interesting effect is what happens to the phase, or if you want to say it the other way, what happens to the period. If you think mechanically, if the spring gets stiffer at large amplitude, then you know that a stiffer spring will produce a faster oscillation. So you would expect that at higher amplitude, the period will be less. And that's right. That's what we can calculate next. If we look at phi dot, well, then we're going to go average epsilon h over r cosine of t plus phi, which will give us average. So the h involves that r cubed cosine cubed. So we're going to cancel out one factor of the r cubed with this factor of r. We end up getting r squared, and then average of cosine to the fourth. And of course, plus order epsilon squared. Now you have to learn what's average of cosine to the fourth. So you can do that with other trig identities. I'll just tell you it comes out to be 3/8. So what does that tell us? If r is constant, think of r as the initial amplitude, then what we've learned is that phi dot is more or less just this 3/8 epsilon times the initial amplitude. Maybe I'll write it as a. Looks more like an amplitude squared. And so what does that mean about the period? Well, look at the angular frequency. The angular frequency you can think of as the time derivative of this whole expression. That is, the omega for the oscillator would be 1 plus phi dot. That is the time derivative of this. So it's 1 plus 3/8 epsilon a squared. That is, the frequency goes up, by the extra correction to the frequency is proportional to the square of the amplitude. Or in terms of the period, you could say 2 pi over omega. That's going to be, to leading order, it would be 2 pi and then 1 minus, you can check, 3/8 epsilon a squared, plus additional correction terms of higher order and epsilon. So it's, as I said, at larger amplitude, the period will be less, but by that exact amount. And it turns out this is, of course, a conservative system. Maybe you noticed that. It's just a spring and a mass. There's no damping. So you can calculate, using conservation of energy, the exact formula for the period. And if you do that exact formula, you'll get some nasty integral. But then you can approximate it for small epsilon, and you'll get the thing that I just wrote down. That is, perturbation theory is giving us the exact result to this order in epsilon. OK, let's stop there.